Welcome to the deep dive. Today we're going to crack open this textbook chapter on something called phase diagrams. I'll admit it sounded a bit dry at first, but then I realized this is the secret code to understanding how any material transforms, from solid to liquid to gas, and
Yeah.
what happens when it transforms, which is huge for engineers, designing everything from bridges to microchips.
What's really fascinating here is that phase diagrams give us this visual map, almost like a GPS, to navigate how a material will behave based on the temperature and what it's mixed with.
Oh, I love a good visual. So our listeners send in excerpts from a material science and engineering textbook, wanting to get a solid grasp on this whole concept.
Yes.
I'm guessing this is foundational stuff for anyone working with materials, right?
Absolutely. Phase diagrams are essential for understanding how to control processes like heat treating, which
Mhm.
basically determines how strong, flexible, or even brittle a material will be.
Okay, so before we get to the heat treating magic, let's start with the basics. What exactly is a phase diagram, and what kind of language are we dealing with here?
Imagine you're making a cake. You've got your ingredients like flour, sugar, eggs. Those are your components in material science lingo. And the whole cake batter, that's your system.
So in our case, the cake could be something like steel, and the ingredients are iron and carbon.
Exactly. Now, within that cake batter, you've got different phases. The flour might clump together a bit, the sugar dissolves, the eggs hold it all together. Each of those is a distinct part of the system with uniform properties.
So like how in a chocolate chip cookie, the dough is one phase and the chocolate chips are another.
Perfect analogy. And just like you wouldn't want your chocolate chips melting into a gooey mess, controlling those phases is crucial in materials.
Okay, that makes sense. So these phase diagrams are showing us what phases exist at different temperatures, right?
Right. And not just temperature, but also composition, how much of each ingredient is present. It's all about finding that sweet spot where the material has the properties we need.
So it's like a map showing us how to get the perfect recipe for our material.
Precisely. But here's where it gets really interesting. Sometimes the most desirable properties don't come from perfectly balanced or what we call equilibrium states.
Equilibrium, so that means everything is stable and happy.
Exactly. But sometimes by shaking things up a bit, we can create what are called metastable states. Think of it like supercooling water. You can get it below freezing but still liquid, even though ice would be the equilibrium state.
So it's like tricking the material into staying in a less stable form. But why would we want to do that?
Because those metastable states can have amazing properties. For example, that supercooled water, if you nudge it just right, will instantly crystallize into ice. That rapid change can be harnessed for things like making super strong metals.
Okay, my mind is officially blown. So how do we actually start deciphering these phase diagrams?
Let's start simple with a one-component diagram. You're familiar with water. We all know it can exist as ice, liquid water, or steam.
Sure, H2O in all its glory.
Well, a pressure temperature phase diagram for water simply maps out those phases and the conditions where they transform. The lines on the diagram represent the boundaries between those phases.
So if you cross a line, you're changing the state of the water.
Exactly. And there's a special point where all three phases, solid, liquid, and gas, coexist in perfect harmony. That's called the triple point. Each substance has its unique triple point.
The triple point, like a magical intersection where everything is possible.
Yeah.
I'm guessing most materials we deal with are a bit more complex than just plain water, though.
You're right. Most engineering materials are alloys mixtures of two or more components. That's where binary phase diagrams come in.
Binary. So now we're dealing with two ingredients in our cake recipe.
Precisely. We keep the pressure constant and focus on how temperature and the proportions of those two components affect the phases present. And here's where the concept of microstructure comes in, how those phases are actually arranged within the material.
Microstructure. So we're zooming in to see how those tiny components are arranged at the atomic level.
Exactly. And that arrangement, believe it or not, determines the strength, flexibility, or brittleness of the material. It's like how the arrangement of bricks determines the strength of a wall.
Okay, so we're not just looking at what phases are present, but also how they're organized.
Right. And this organization can change dramatically depending on how quickly we cool the material from a liquid state.
So the speed of cooling matters. That's interesting.
It's crucial. If we cool too quickly, the atoms might not have time to arrange themselves neatly, and we end up with a less stable but potentially stronger structure.
So it's like a race against time for those atoms to find their perfect spots.
Exactly. Now let's dive into a specific type of binary system called isomorphous, where the two components mix perfectly in both liquid and solid states.
Isomorphous, that sounds like a mouthful. Any relatable examples?
Think of sugar dissolving in water. You can add a little or a lot, and it all mixes perfectly to form a single uniform solution.
Okay, I can picture that. So an isomorphous alloy would be like a perfect blend of two metals.
Precisely. A classic example is the copper-nickel system. Their phase diagram has what we call a liquidus line, above which everything is liquid, and a solidus line below which everything is solid.
And between those lines.
We have a mix of liquid and solid phases coexisting. Imagine a slushy. You've got both liquid and solid ice mixed together.
A metallurgical slushy. I love it. But how do we figure out exactly how much of each phase we have in that mixed region?
We use a clever tool called a tie line. It's a horizontal line that we draw across the two-phase region on the diagram. The points where it intersects the liquidus and solidus lines tell us the exact composition of each phase.
So the tie line is like connecting the dots to decode the composition.
Exactly. And to calculate the relative amounts of each phase, we use something called the lever rule.
The lever rule sounds intriguing.
Imagine a seesaw. The fulcrum is the overall alloy composition, and the ends of the seesaw represent the compositions of the two phases. The distances from the fulcrum to each end tell us the proportions of each phase. The longer the lever arm, the more of that phase you have.
Okay, so it's all about balance. The longer the lever arm, the heavier the load, or in this case, the greater the amount of that phase.
Precisely. Now, remember how I said the cooling rate is important? Well, in real-world scenarios, cooling isn't always perfectly slow and balanced. And that can lead to something called coring.
Coring, like the core of an apple.
In a way, yes. Imagine each grain of the material as a tiny apple. If cooling is slow, the composition within each grain is uniform like a perfectly mixed applesauce. But if cooling is fast, the center of the grain, which solidifies first, might have a different composition from the outer edges.
So it's like having a different flavor of applesauce in the center of each apple.
A great analogy. And this coring can significantly affect the material's properties. It can make it weaker or cause it to melt prematurely at those grain boundaries.
So how do we fix this coring problem? Can we blend it all back into a uniform applesauce?
We can. A homogenization heat treatment can even out the composition. We basically heat the alloy below its melting point to allow the atoms to diffuse and rearrange themselves more evenly.
Homogenization, it's like giving those atoms a second chance to find their perfect spots. Amazing how much control we have over these materials at the microscopic level.
It is truly remarkable, and understanding these concepts is just the beginning of the journey into the world of phase diagrams.
This is already so much more interesting than I thought it would be. I can't wait to see what other secrets these diagrams hold.
We'll buckle up, because we're just getting started. Next, we'll explore what happens when those components don't mix so perfectly, leading us to the fascinating world of eutectic systems.
All right, so we've explored like the world of perfect mixing, with those isomorphous systems. But I have a feeling like things get a lot more complex, out in the real world. What happens when our ingredients aren't so eager to blend together?
That's where things get really interesting. Let's dive into eutectic systems where the components have limited solubility in each other when they're in solid form. Think like oil and water, they just don't want to mix.
So instead of like a smooth blend, we get more of a separation.
Exactly. A classic example is the copper-silver system. Their phase diagram has a special point called the eutectic point, where something really fascinating happened.
The eutectic point sounds dramatic. What goes down there?
Imagine you're cooling down a liquid mixture of copper and silver. As you reach the eutectic temperature, bam! The liquid transforms directly into two distinct solid phases, forming these beautiful layered structures.
Right, so it's not just a random mix of solid copper and silver. They organize themselves into layers.
That's right. It's all about efficiency at the atomic level. Those layers form because it minimizes the distance atoms have to travel during the transformation. It's like nature's way of finding the most efficient packing arrangement.
Nature's a pretty smart organizer, I'll give it that.
Yeah.
Any real-world examples where we see this eutectic magic in action?
Absolutely. Think about soldering. Lead tin solders are classic eutectic alloys. They have a low melting point due to their eutectic composition, making them perfect for joining electronic components.
So that's why my soldering iron melts the solder so easily.
Yeah.
It all comes back to those eutectic phase diagrams. It's like having the cheat code for getting those metals to cooperate.
Exactly. Now, as we venture into even more complex alloy systems, we encounter intermediate phases and compounds, which add another layer of intrigue to our phase diagrams.
Intermediate phases and compounds sounds like we're bringing in some new characters to our metallurgical party.
Precisely. Unlike solid solutions where the components mix freely, these guys have specific chemical formulas and their own unique properties.
So they're like the VIP guests with reserved seating on our phase diagram.
A great way to put it. For instance, in the magnesium lead system, we find an intermetallic compound called Mg2Pb. It has a fixed composition and shows up as a vertical line on the diagram.
So it's like a new component adding another dimension to our understanding.
Exactly. And as we add more components, our phase diagrams become more intricate, like a tapestry woven with different phases, boundaries, and reactions.
Okay, my brain is starting to feel a little full. Is there any way to simplify this complexity, some sort of like guiding principle?
There is. It's called the Gibbs phase rule, and it's like a master key for unlocking the secrets of phase equilibria.
The Gibbs phase rule sounds like something out of a physics textbook.
It might sound intimidating, but it's actually a pretty simple concept. It's an equation that helps us determine how many phases can coexist at equilibrium in a given system. Think of it like a balancing act between the number of phases, the components present, and the degrees of freedom we have.
Degrees of freedom, so how much we can tweak things like temperature and composition without messing up the whole system.
Exactly. In a single phase region, like a pure liquid or solid, we have more freedom to change things. But as we add more phases, our freedom gets restricted.
So it's like a game of Jenga. The more blocks you pull out, the less stable the tower becomes.
A perfect analogy. And at the eutectic point where we have three phases coexisting, we have 0 degrees of freedom. Everything is fixed, the temperature and the compositions of all three phases.
0 degrees of freedom sounds a bit claustrophobic for those atoms.
It does, but it also means we have a very precise set of conditions for that three-phase coexistence. And the Gibbs phase rule helps us understand and predict these conditions.
Okay, I think I'm starting to get a handle on this phase rule thing. But before we move on, can we take a quick detour and talk about ceramic materials? They're not metals, but I'm guessing phase diagrams are still relevant.
Absolutely. Phase diagrams are crucial for understanding and designing ceramics for various applications, from high-temperature engine components to delicate electronic substrates.
So those beautiful ceramic tiles in my bathroom, their existence is all thanks to phase diagrams.
You could say that. And when we delve into the world of ternary systems with three components, things get even more complex. Instead of a flat 2D diagram, we need a 3D model to represent all the possible combinations.
3D phase diagram sounds like a challenge even for seasoned material scientists.
It can be, but the fundamental principles remain the same. We're still mapping out those phases, boundaries, and transformations just in a more complex space.
Okay, so ceramic and ternary systems check. Now I think we're ready to tackle the main event, the iron-carbon system. The backbone of steelmaking, right?
You got it. The iron-carbon phase diagram is the foundation for understanding a vast array of alloys that shape our modern world. From the skyscrapers that pierce the sky to the cars we drive, it all starts with this diagram.
The iron-carbon system, it's like the grand finale of our phase diagram journey.
Get ready for a wild ride through the world of ferrite, austenite, cementite, and the legendary pearlite. We'll uncover the secrets of heat treatment and how it transforms iron and carbon into a symphony of materials with incredible strength and versatility.
Ferrite, austenite, pearlite. It sounds like a metallurgical orchestra. I'm on the edge of my seat.
Let's dive in. The iron-carbon system starts with pure iron, which can exist in different forms depending on the temperature. At room temperature, it's in a form called ferrite, also known as alpha iron.
Ferrite. So that's our starting point, the base note of our metallurgical symphony.
Exactly. Ferrite has a body-centered cubic BCC crystal structure and can only dissolve a tiny amount of carbon. Think of it like a tightly packed box with only a few small spaces for carbon atoms to squeeze in.
So ferrite is like the minimalist of the iron world, happy with just a touch of carbon.
Precisely. But as we heat things up, iron undergoes a fascinating transformation. At around 912 degrees Celsius, it changes its crystal structure to a face-centered cubic FCC arrangement, becoming what we call austenite, or gamma iron.
Austenite, a change in crystal structure, sounds like things are getting a bit more spacious.
Exactly. Austenite is like a mansion compared to ferrite's tiny apartment. It has much more space within its crystal lattice, allowing it to dissolve a significantly larger amount of carbon.
So austenite is the party host welcoming all those carbon atoms with open arms.
A great way to visualize it. And this ability to dissolve carbon is crucial for steelmaking because the amount of carbon in austenite determines the final properties of the steel.
Okay, so we've got our ferrite and our austenite, each with its own carbon holding capacity. What happens next in this metallurgical dance?
Well, as we cool austenite back down, things get really interesting. The solubility of carbon in iron decreases, and those extra carbon atoms have to go somewhere.
So it's like the party's over and those carbon atoms are looking for a place to crash.
Exactly. If we cool austenite slowly, it will transform back into ferrite, but the excess carbon will combine with iron to form a new phase called cementite.
Cementite, a new character enters the stage. What's its role in this play?
Cementite, also known as iron carbide, Fe3C, is a hard and brittle compound. Think of it like the strong, silent type. It doesn't say much, but it plays a crucial role in giving steel its strength.
So as austenite cools, it kicks out some of its carbon, which forms ferrite, and the remaining carbon teams up with iron to form cementite.
Precisely. But here's where the story takes another fascinating turn. At a specific temperature called the eutectoid temperature, austenite can transform into a unique structure called pearlite.
Pearlite, I've heard of that. Isn't that what gives steel its characteristic strength and toughness?
You're absolutely right. Perlite is a layered structure composed of alternating layers of ferrite and cementite. Imagine a stack of pancakes. That's essentially what perlite looks like under a microscope.
A stack of metallurgical pancakes. I love it. But why does it form these layers instead of just a random mix of ferrite and cementite?
It all comes down to diffusion, the movement of atoms. During the eutectoid transformation, carbon atoms have to redistribute themselves. Forming these layers minimizes the distance they have to travel, making the process more efficient.
So it's like nature's way of optimizing the transformation process, creating a beautifully organized structure in the process. Amazing.
It is truly remarkable. Now, the type of microstructure that forms in steel depends on the carbon content and the cooling rate. If we have less carbon than the eutectoid composition, which is 0.76 weight percent carbon, we get something called hypotectoid steel.
Hypertectoid, so less carbon, less pearlite.
Exactly. In hypoeutectoid steel, we get perlite, along with some leftover ferrite that formed before the eutectoid transformation. Imagine islands of perlite embedded in a sea of ferrite.
A metallurgical archipelago. And what about steels with more carbon than the eutectoid composition?
Those are called hypereutectoid steels. In this case, we have more cementite than ferrite, so we get perlite surrounded by a network of cementite. Think of it like continents of cementite with perlite filling in the gaps.
So it's like flipping the script. Instead of islands, we have continents.
Exactly. And by controlling the cooling rate, we can fine-tune the size and distribution of these microstructural features, tailoring the properties of the steel for different applications.
This is incredible. So by carefully controlling the carbon content and the cooling rate, we can create a whole spectrum of steel microstructures, each with its own unique set of properties. It's like having a metallurgical toolbox.
Precisely. But the story doesn't end there. Adding other alloying elements like chromium, nickel, or molybdenum can further enhance the properties of steel and create an even wider range of possibilities. Wait, we can add even more ingredients to this metallurgical mix. Sounds like things are about to get even more complex and exciting.
You're absolutely right. Adding these alloying elements can shift the eutectoid point, change the solubility limits of carbon, and even introduce new phases, creating an almost infinite variety of steel alloys with unique characteristics.
My mind is officially blown. So from the simple elegance of ferrite to the layered beauty of perlite, the iron-carbon system is a symphony of material science waiting to be conducted by skilled engineers.
A beautiful way to put it. And it all starts with understanding the language of phase diagrams. They are the key to unlocking the secrets of steel and designing the materials that shape our world.
This has been an incredible journey so far. I'm starting to see why phase diagrams are considered the Rosetta Stone of material science.
They truly are. And remember, we've only scratched the surface of this fascinating field. There's a whole universe of materials out there, each with its own unique phase diagram and story to tell. Well, on that note, I think it's time for a little break. But stay tuned, because when we come back, we'll explore how these phase diagrams help us navigate the real world of non-equilibrium conditions and uncover the secrets of metastable states. It's going to be epic. All right, we're back and ready to tackle like the final frontier of phase diagrams, those mysterious non-equilibrium states. I have to admit, this is where I start to feel like we're venturing into the unknown.
It's true that non-equilibrium conditions can seem a bit chaotic, but remember, even in chaos, there's an underlying order. And phase diagrams, even though they primarily depict equilibrium states, still provide a crucial foundation for understanding these dynamic processes.
So it's like having a map of a well-planned city, but sometimes you have to go off-roading to find hidden gems.
Exactly. The phase diagram is our roadmap, but real-world processes often deviate from that ideal path. Things like cooling rates, impurities, and other factors can throw a wrench into the equilibrium equation and lead to the formation of metastable states.
Metastable states, they're like the rebels in the materials world, defying the rules of equilibrium.
In a way, yes. They're phases that exist outside of the typical equilibrium conditions, often possessing unique and highly desirable properties.
Okay, so let's dive into a specific example. You mentioned martensite earlier. It's a metastable phase of steel known for its incredible strength, right?
Exactly. Martensite forms when austenite, that high-temperature form of iron, is cooled extremely rapidly, so rapidly that the carbon atoms don't have time to diffuse and form those nice, neat layers of pearlite.
So it's like hitting the pause button on the transformation process, freezing those carbon atoms in place.
A perfect analogy. And that creates a highly distorted, strained crystal structure that makes martensite incredibly hard and strong, but also brittle.
So it's a trade-off strength for flexibility.
Hmm.
But it sounds like a worthwhile trade-off for certain applications.
Absolutely. Martensite is used in everything from knives and swords to automotive parts and aerospace components where high strength and wear resistance are critical.
Wow. So even though martensite doesn't appear on the equilibrium phase diagram, understanding those diagrams is still crucial for creating this incredible material.
Precisely. The phase diagram is the foundation, but our knowledge of non-equilibrium phenomena like diffusion rates and transformation kinetics allows us to manipulate these processes and achieve desired microstructures.
So it's like having a recipe but knowing how to adjust the cooking time and temperature to create a whole new dish.
A brilliant analogy. And the world of non-equilibrium processing is vast and ever-evolving. From the formation of metallic glasses to the growth of nanomaterials, we're constantly pushing the boundaries of what's possible by manipulating materials at the atomic level.
It's like we're moving from a world of static blueprints to a world of dynamic, ever-changing systems. And phase diagrams are the key to navigating this complexity.
Exactly. And with that, I think we've covered the essential elements of phase diagrams. From the basic concepts of phases and equilibrium to the intricacies of non-equilibrium phenomena, we've journeyed through the fascinating landscape of material transformations.
This deep dive has been an absolute revelation. I feel like I've gained a whole new appreciation for the intricate world of material science and the power of phase diagrams.
I'm thrilled to hear that. And remember, this is just the beginning of your exploration. The world of materials is vast and constantly evolving with endless possibilities for discovery and innovation.
Well, on that inspiring note, we'll wrap up this deep dive into phase diagrams. To our listeners, thank you for joining us on this intellectual adventure. We hope you've gained a newfound appreciation for the hidden world of material transformations and the elegant language of phase diagrams.
And remember, the next time you encounter a material, whether it's the steel in your car or the ceramic in your coffee mug, take a moment to think about the fascinating journey it took to become what it is. It's a story written in the language of phase diagrams, a testament to the power of human ingenuity and the endless wonders of the material world.
Until next time, keep exploring, keep questioning, and keep diving deep into the world of knowledge. See you on our next deep dive.